Hello future engineers, we are down to the second to the last video presentation for ENG 201. This is part 1 for module 4.3 on nuclear chemistry.
This PowerPoint presentation is developed based from the following references.
For module 4.3, we have the following intended learning outcomes. First, we are to write balanced nuclear equations for radioactive decay and nuclear transformation processes. 2. We are to differentiate chemical reactions from nuclear reactions. 3. We are to compare relative stabilities of given nuclei by applying stability rules. 4. We are to predict using the N/P ratio where a given isotope will decay by beta decay or positron decay. 5. We are to calculate the nuclear binding energies. 6. We are also to predict the product resulting from neutron capture by a given isotope, which is then followed by a beta decay. Then 7. We are to describe both fission and fusion, and to relate these processes to the curve of binding energy per nucleon.
Nuclear chemistry is the study of reactions involving changes in atomic nuclei. This branch of chemistry began in the discovery of natural radioactivity by Antoine Becquerel and grew as a result of subsequent investigations by Pierre and Marie Curie and many others. Nuclear chemistry is very important in the news today. In addition to applications in the manufacture of atomic bombs, hydrogen bombs, and neutron bombs, even the peaceful use of nuclear energy has become controversial, in part because of safety concerns about nuclear power plants and also because of problems with radioactive waste disposal. Module 4.3.1 The Nature of Nuclear Reactions. Let us start this topic by discussing some basic concepts. Recall the structure of the atom. Here, consider the atom of helium. Atoms are composed of subatomic particles, protons, neutrons, and electrons. Protons and neutrons are located in the nucleus and provide most of the mass of the atom, while electrons circle the nucleus in shells and subshells and account for an atom's size. With the exception of hydrogen 1, all nuclei contain two kinds of fundamental particles called the protons and neutrons. Also, remember the notation for succinctly representing an isotope of a particular atom. The element in this example, represented by the symbol C, is carbon. Its atomic number, noted as Z, is 6, and it is the lower left subscript on the symbol and is the number of protons in the atom. The mass number, represented by A, is the superscript to the upper left of the symbol. It is the sum of the number of protons and neutrons in the nucleus of this particular isotope. In this case, the mass number is 12, which means that the number of neutrons in the atom is 12 minus 6. That is, the mass number of the atom minus the number of protons in the nucleus equals the number of neutrons. Occasionally, the atomic number is omitted in this notation because the symbol of the element itself conveys its characteristic atomic number.
The two general kinds of nuclear reactions are nuclear decay reactions and nuclear transmutation reactions. In a nuclear decay reaction, also called as radioactive decay, an unstable nucleus emits radiation and is transformed into the nucleus of one or more other elements. The resulting daughter nuclei have a lower mass and are lower in energy or more stable than the parent nucleus that decayed. In contrast, in a nuclear transmutation reaction, a nucleus reacts with a subatomic particle or another nucleus to form a product nucleus that is more massive than the starting material. As we shall see, nuclear decay reactions occur spontaneously under all conditions, but nuclear transmutation reaction occurs only under special conditions, such as the collision of a beam of highly energetic particles with a target nucleus or in the interior of stars. We begin this section by considering the different classes of radioactive nuclei along with their characteristic nuclear decay reactions in the radiation they emit. Radioactive decay and nuclear transmutations are nuclear reactions which differ significantly from ordinary chemical reactions. This table summarizes the differences. First, in chemical reactions, no new elements can be produced. Whatever elements you have on the reactant are the elements that you can also find on the product. However, in nuclear reactions, these elements may be converted from one element to another. Second difference involves the particles. So, usually in a chemical reactions, only the outermost electrons participate in reactions. In nuclear reactions, particles within the nucleus, such as the protons and neutrons, are involved in the reactions. Thirdly, with regard to the energy, so chemical reactions release or absorb relatively smaller amounts of energy, while nuclear reactions release or absorb immense amounts of energy, typically 1,000 times more than that in a chemical reaction. Then, lastly, the rates of reaction for chemical reactions depends on factors such as concentration, pressure, temperature, and catalyst, while in nuclear reactions, the rates of reactions are not influenced by external factors.
Balancing nuclear equations. To discuss nuclear reactions in any depth, we need to understand how to write and balance the equations. Writing a nuclear equation differs somewhat from writing equations for chemical reactions. In addition to writing the symbols for various chemical elements, we must also explicitly indicate protons, neutrons, and electrons. In fact, we must show the numbers of protons and neutrons present in every species in such an equation. The symbols for elementary particles are as follows. In accordance with the notation, the superscript in each case denotes the mass number or the total number of neutrons and protons present, and the subscript is the atomic number or the number of protons. Thus, the atomic number of a proton is 1 because there is one proton present, and the mass number is also 1 because there is one proton but no neutrons present. On the other hand, the mass number of a neutron is 1 but its atomic number is 0 because there are no protons present. For the electron, the mass number is 0 because there are neither protons nor neutrons present, but the atomic number is -1 because the electron possesses a unit negative charge. There are two symbols for the electrons here. The one on the left, as 0, -1 e, represents an electron in or from an atomic orbital. The symbol on the right, represented by 0, -1 beta, represents an electron, although physically identical to any other electron, comes from a nucleus in a decay process in which a neutron is converted to a proton and an electron, and not from an atomic orbital. The positron has the same mass as the electron, but bears a +1 charge. Then, we have the alpha particle that has 2 protons and 2 neutrons, so its atomic mass is 2 and its mass number is 4. Like chemical reactions, nuclear equations need to be balanced, and in doing so, we apply these two rules. First is the conservation of the mass number A. It says that the sum of the protons plus neutrons in the products must equal the sum of the protons plus neutrons in the reactants. The second rule is the conservation of the atomic number Z or the nuclear charge. It says that the sum of the nuclear charges in the products must equal the sum of the nuclear charges in the reactants. In a nutshell, this can be summarized in this equation. Okay. If the atomic number and the mass number of all but one of the particles in a nuclear reaction are known, we can identify the particle by balancing the reaction. For instance, we could determine that oxygen-17 is a product of the nuclear reaction of nitrogen-14 and the alpha particle, if we know that a proton was one of the two products. Let us apply these rules to these examples. Balance the following nuclear equations. That is, identify the product X. Given A, polonium-212, producing lead-208 and product X, and cesium-137, producing barium-137 and product X. Just note that in balancing nuclear equations, the sum of the atomic numbers and that of the mass numbers must match on both sides of the equation. Let us now try to answer the given example. So first, we have polonium-212 being converted to lead-208 and element X. Here, the mass number and atomic number are 212 and 84 respectively on the left-hand side and 208 and 82 respectively on the right-hand side. Applying our rules of balancing the atomic number and mass number, okay, we balance the mass number by subtracting 208 from 212, and we balance the atomic number by subtracting 82 from 84. This results to an X that must have a mass number of 4 and an atomic number of 2, which means that this is an alpha particle. Okay. Enclosed here is the balance equation for this nuclear reaction. Another case is the conversion of cesium-137 to barium-137. In this case, the mass number is the same on both sides of the equation, but the atomic number of the product is one more than that of the reactant. Thus, X must have a mass number of 0 and an atomic number of -1, which means that this is an electron, okay, represented by 0, -1, beta. Enclosed here is the balance equation for the said nuclear equation. Here is another example that will allow us to apply these rules. Here, uranium-238, a radioactive material undergoing nuclear reaction in which helium-4 nuclei are spontaneously emitted. When a uranium-238 nucleus loses an alpha particle, the remaining fragment is thorium-234 nucleus with an atomic number of 90 and a mass number of 234. The nuclear reaction is given in this manner. Now just to check that the rules are applied, we have A as the mass number, which sums up to 238 on the left side and also 238 on the right side, being a result of 234 plus 4. And the atomic number, which is 92 for uranium, is just going to be equal to the sum of 90 and 2. Thus, the rules are applied. Let us now discuss nuclear stability. Nuclear stability means that the nucleus of an element is stable and thus it does not decay spontaneously, emitting any kind of radioactivity. Among the 9,000 nuclei expected to exist and the 3,000 presently known, only 195 are stable against spontaneous decay. The nucleus occupies a very small portion of the total volume of an atom, but it contains most of the atom's mass because both the protons and the neutrons reside there. In studying the stability of the atomic nucleus, it is helpful to know something about its density, because its density tells us how tightly the particles are packed together. The density of a nucleus roughly containing 30 protons and 30 neutrons and having a radius of 5 times 10 to the minus 3 picometer and a mass of 1 times 10 to the negative 22 grams is 2 times 10 to the positive 14 grams per cubic centimeter. This is an extremely high density. The highest density known for an element is only 22 grams per cubic centimeter for the element osmium. Thus, the average atomic density is roughly 9 times 10 to the 12, or 9 trillion times more dense than the densest element known. The enormous high density of the nucleus prompts us to wonder, what holds the particles together so tightly? From Coulomb's law, we know that like charges repel and unlike charges attract one another. We would thus expect the protons to repel one another strongly, particularly when we consider how close they must be to each other. This indeed is so. However, in addition to the repulsion, there are also short-range attraction between proton and proton, proton and neutron and neutron. The stability of any nucleus is determined by the difference between the Coulombic repulsion and the short-range attraction. If repulsion outweighs attraction, the nucleus disintegrates, emitting particles and/or radiation. If attractive forces prevail, the nucleus is stable.
The principal factor that determines whether a nucleus is stable is the neutron-to-proton ratio, or N/B. For stable atoms of elements having low atomic number, the N/B value is close to 1. As the atomic number increases, the neutron-to-proton ratios of the stable nuclei become greater than 1. This deviation at higher atomic numbers arises because a larger number of neutrons is needed to counteract the strong repulsion among the protons and stabilize the nucleus. Thus, here, all isotopes of elements with atomic numbers higher than 83 are unstable and radioactive. Another determinant whether a nucleus is stable is given by the nuclear magic numbers. Nuclei that contain 2, 8, 20, 50, 82, or 126 protons or neutrons are generally more stable than nuclei that do not possess these numbers. For example, there are 10 stable isotopes for theme with the atomic number of 50 and only 2 stable isotopes for antimony with the atomic number 51. The numbers 2, 8, 20, 50, 82, and 126 are called magic numbers. The significance of these numbers for nuclear stability is similar to the number of electrons associated with the very stable noble gases, that is 2, 10, 18, 36, 54, and 86 electrons. The following are some examples of nuclei that utilizes these magic numbers. Another indicator for nuclear stability is given by the odd-even rule. It says that nuclei with even numbers for both protons and neutrons are generally more stable than those with odd numbers of these particles. The table shows to us the pattern of the stability. When number of neutrons and protons in a nucleus are both even, the isotope is far more likely to be stable when both numbers are odd. Also, although rare, we have 4 stable odd-odd nuclides given by hydrogen 2, lithium 6, boron 10, and nitrogen 14. More on nuclear stability. So the figure shows a plot of the number of neutrons on the y-axis versus the number of protons on the x-axis in various isotopes. The stable nuclei are located in an area of the graph known as the belt of stability. Most radioactive nuclei lie outside this belt. Above the stability belt, the nuclei have higher neutron-to-proton ratios than those within the belt for the same number of protons. The belt of stability generally has a neutron-to-proton ratio larger than 1. When the neutron to proton ratio is too large, beta decay will occur. And when the neutron to proton ratio is too small, positron decay or electron capture will occur. Let us try to check understanding and work on this given example. The following isotopes are unstable. Use the figure to predict whether they will undergo beta decay or positron emission. Also, write a nuclear equation for each case. Let us work on this example by considering boron-13. So checking on the periodic table, boron has an atomic number of 5, and thus on the x-axis we can plot that line that corresponds to 5 protons. Consequently, with a given mass number, we can also find a value on the y-axis that gives the number of neutrons. Subtracting 13 with 5, we have 8 as the number of neutrons for the given isotope. Now we see the intersection of the line that corresponds to a point that is above the given stability belt. Okay. This will allow us to decide that in order for this given isotope to become stable, it has to undergo a beta decay. And once that is done, we can have this nuclear equation. Now for part B, we are given gold. We do the same process. We check on the atomic number of gold from the periodic table, and we can see that it has 79 as its atomic number, thus the number of protons. And then from the given mass number of 188, we can compute for the number of neutrons to be 109. So we plot this value on the y-axis. Again, we have this point of intersection for the proton and the neutron, which we can find to be lying under or below the given stability belt. Thus, from here, we can say that this has to undergo positron emission to become stable. And we have this given equation. Let us answer example 2. Here we are to predict the kind of nuclear change that each unstable nuclide undergoes when it decays, given its atomic mass and mass number. For number 1, we have titanium-45. So this nuclide has a neutron to proton ratio of only 1.05, which is much less than the requirement for stability for an element with an atomic number in this range. Nuclei that have low neutron to proton ratios decay by converting a proton to a neutron, and this can be done through positron emission or electron capture. By positron emission, it converts a proton to a neutron and a positron, and by electron capture, it converts a proton and a core electron to a neutron. In this case, both are observed, with the positron emission occurring about 86% of the time and electron capture about 14% of the time. For item 2, we have plutonium-292. From our rules, nuclei with an atomic number greater than 83 are too heavy to be stable and usually undergo alpha decay, which decreases both the mass number and the atomic number. Thus, it is expected to decay by alpha emission. For problem 3, we have boron-12. This nuclide has a neutron to proton ratio of 1.4, which is very high for a light element. Nuclei with high neutron to proton ratios decay by converting a neutron to a proton and an electron. The electron is emitted by a beta particle and the proton remains in the nucleus, causing an increase in the atomic number with no change in the mass number. Therefore, we predict that for boron-12, it will undergo beta decay. So for the next two items, we have their corresponding NT ratios and decays. This is just another slide for you for the same concept. Let us work on a different example in example 3. Here we are given pairs of isotopes and we are to indicate which one would we expect to be radioactive. For the first pair, we have neon-20 and neon-17. Here neon-17 should be radioactive. It falls below the belt of stability, having a low N/P ratio. For the second pair, we have calcium 40 and calcium 45. Between the two, calcium 45 should be radioactive because it falls above the belt of stability, having high N/P ratio. Then for C, between molybdenum and technetium, we are to expect that all technetium isotopes are radioactive. Then for the fourth pair, for mercury, mercury 195 should be radioactive. Mercury 196 has an even number for both neutrons and protons, so thus it's more stable. Now, for the fifth one, all curium isotopes are unstable. Now let's move on to the next module, module 4.3.2, natural radioactivity. Nuclei outside the belt of stability, as well as nuclei with more than 83 protons, tend to be unstable. The spontaneous emission by unstable nuclei of particles or electromagnetic radiation or both is known as radioactivity. The main types of radiation are alpha particles for doubly charged helium nuclei, beta particles or electrons, gamma rays, which are very short wavelength electromagnetic waves, positron emission, and electron capture. First in the list of natural radioactivity is alpha decay. So alpha decay is the emission of an alpha particle from the nucleus. For example, polonium-210 undergoes alpha decay as it creates lead-206. Alpha decay occurs primarily in heavy nuclei with mass numbers greater than 200 and atomic numbers greater than 83. Because the loss of an alpha particle gives a daughter nuclei with a mass number 4 units smaller and an atomic number 2 units smaller than those of the parent nuclide, the daughter nuclide has a larger N/P ratio than the parent nuclide. If the parent nuclide undergoing a decay lies below the band of stability, the daughter nuclide will lie closer to the band. Next, we have beta decay. Beta decay is the emission of an electron from a nucleus. Iodine 131 is an example of a nuclide that undergoes beta decay. Beta decay, which can be thought of as the conversion of a neutron into a proton and a beta particle, is observed in nuclides with a large N/P ratio. The beta particle, or the electron emitted, is from the atomic nucleus and not one of the electrons surrounding the nucleus. Such nuclei lie above the bond of stability. Emission of an electron does not change the mass number of the nuclide, but does increase the number of its protons and decrease the number of its neutrons. Consequently, the N/P ratio is decreased, and the daughter nuclei lies closer to the band of stability than did the parent nuclide. Gamma emission is observed when a nuclide is formed in an excited state and then decays to its ground state with the emission of a gamma ray. The presence of a nucleus in an excited state is often indicated by an asterisk. Cobalt-60 emits gamma radiation and is used in many applications, including cancer treatment. There is no change in mass number or atomic number during the emission of a gamma ray, unless the gamma emission accompanies one of the other modes of decay. Positron emission or beta plus decay is the emission of a positron from the nucleus. Oxygen-15 is an example of a nuclide that undergoes positron emission. Positron emission is observed for nuclides in which the neutron-proton ratio is low. These nuclides lie below the band of stability. So position decay is the conversion of a proton into a neutron with the emission of a positron. The neutron-to-proton ratio increases, and the daughter nuclide lies closer to the band of stability than did the parent nuclide. Then last in the list is electron capture. Electron capture occurs when one of the inner electrons in an atom is captured by the atom's nucleus. For example, potassium-40 undergoes electron capture. Electron capture occurs when an inner shell electron combines with a proton and is converted into a neutron. The loss of an inner shell electron leaves a vacancy that will be filled by one of the outer electrons. As the outer electron drops into the vacancy, it will emit energy. In most cases, the energy emitted will be in the form of an X-ray. Like positron emission, electron capture occurs for proton-rich nuclei that lie below the band of stability. Electron capture has the same effect on the nucleus as does as positron emission. That is, the atomic number is decreased by 1 and the mass number does not change. These increase the neutron to proton ratio, and the daughter nuclide lies closer to the bond of stability than did the parent nuclide. Whether electron capture or positron emission occurs is difficult to predict. The choice is primarily due to kinetic factors, with the one requiring the smaller activation energy being the more likely to occur. This figure summarizes these types of decay along with their equations and changes in the atomic mass and mass numbers. Now let's have radioactive decay series. The naturally occurring radioactive isotopes of the heaviest elements fall into the chains of successive disintegrations or decays, and all the species in one chain constitute a radioactive family or radioactive decay series. Three of this series include most of the naturally radioactive elements in the periodic table, and they are the uranium series, the actinide series, and the thorium series. Each series is characterized by a parent or first member that has a long half-life and a series of daughter nuclides that ultimately lead to a stable end product that is a nuclide on the band of stability. In all three series, the end product is a stable isotope of lead. In this slide, we also have presented the uranium-238 decay series, consisting of 14 separate steps before producing the stable lead-206. This series consists of 8 alpha decays and 6 beta decays. Let us try to further understand the radioactive decay series by working on this example that requires us to fill in the given blanks. Note that for this example, we are going to be dealing with the alpha particle and the beta particle. Okay. So for the first series, we start with thorium-232 and it undergoes an alpha decay. So we expect that the mass number and the atomic number would be changing by 4 or decreasing by 4 and 2 respectively. So creating radon-228. Then after undergoing beta emission, we expect that there should be no change in the mass number. However, the atomic number would change and would be increased by 1. So from radon, we will be having actinium. Okay. Now, this actinium would undergo another beta series, thus we will have to increase its atomic number again by 1. Now, for the second series, we have uranium-235. It undergoes alpha emission once more. So there will be a change in the mass number by 4 and in the atomic number by 2. So resulting in the creation of thorium-231. This undergoes beta emission, which will cause its atomic number to change and increase by 1 again, so creating now palladium-231. This palladium undergoes alpha decay, and therefore it will be increasing its or decreasing its mass number by 4 and its atomic number by 2. Then last in the series, we are to start with the given palladium-233. So this is a result of a decay, of an alpha decay from an unknown isotope. So instead of decreasing the atomic number and the mass number, we will try to increase it. So from 233, we add 4 in the mass number, and in the atomic number, we will be adding 2. And this will actually result to neptune 237. Now, from palladium 233, it undergoes beta emission. And again, by beta emission, there's kind of an increase in the atomic number by 1. So from 91, we will have 92. Okay, so this results to uranium 233, which would still undergo an alpha decay. So there would be, we expect a decrease in the mass number and atomic number by 4 and 2 respectively, resulting to the creation of thorium-229. Next slide will be about module 4.3.3 or mass defect and binding energy. Let us now have a quantitative measure of the nuclear stability through the nuclear binding energy, which is the energy required to break up a nucleus into its component protons and neutrons. This quantity represents the conversion of mass to energy that occurs during an exothermic nuclear reaction. The concept of nuclear binding energy evolved from studies of nuclear properties, showing that the masses of nuclei are always less than the sum of the masses of the nucleons, which is a general term, by the way, for the protons and neutrons in a nucleus. If we consider, for example, the isotope of fluorine-19, and that it actually has an atomic mass of 18.9984 atomic mass unit. So the nucleus has 9 protons and 10 neutrons, and therefore a total of 19 nucleons. So using the known masses of the proton at 1.007825 atomic mass unit, and that of the neutron at 1.08665 atomic mass unit, we can proceed with the following analysis: that the mass of the 9 protons is equal to 9.070425 atomic mass unit, and that of the 10 neutrons, we will have 10.08665 atomic mass unit. And therefore, the atomic mass of this isotope of fluorine, calculated from the known numbers of electrons, protons, and neutrons, is 19.15708, which is larger than the measured mass of the fluorine-19 isotope of 18.9984. So the difference between the mass of an isotope and the sum of the masses of its protons, neutrons, and electrons is called as the mass defect. And for this case, this has a value of 0.1587 atomic mass unit. Relativity theory tells us that the loss in mass shows up as energy or heat given off to the surroundings. Thus, the formation of fluorine-19 is exothermic. Einstein's mass to energy equivalence relationship states that E is equal to mc squared, where E is energy, m is mass, and c is the speed of light. We can calculate the amount of energy released by writing delta E is equal to delta m times c squared, where delta E and delta m are defined as follows. Delta E is equal to the energy of the product minus the energy of the reactants, and delta m is the mass of the product minus the mass of the reactants. Thus, the change in mass for our fluorine-19 is given by delta m, which is equal to 18.9984 atomic mass unit minus 19.15708 atomic mass unit. This results to a negative 0.1587 atomic mass unit difference in mass. Now, because fluorine-19 has a mass that is less than the mass calculated from the number of electrons and nucleons present, delta m is a negative quantity. Consequently, delta E is also a negative quantity. That is, energy is released to the surroundings as a result of the formation of the fluorine-19 nucleus. So we calculate delta E as follows. That delta E is equal to negative 0.1587 atomic mass unit times the speed of light. Okay? Thus, we have a negative 1.43 times 10 to the 16 atomic mass unit meter squared per second squared. Now, to express this in joule, we use the following conversion factors and obtain a negative 2.37 times 10 to the minus 11 joules of energy. This computed delta E is the amount of energy released when one fluorine-19 nucleus is formed from 9 protons and 10 neutrons. The nuclear binding energy of the nucleus is 2.37 times 10 to the minus 11 joules, which is the amount of energy needed to decompose the nucleus into separate protons and neutrons. In the formation of 1 mole of fluorine nuclei, for instance, the energy release is given by the computed delta E multiplied by Avogadro's number. So this allows us to determine the energy per mole. So for this fluorine-19, the nuclear binding energy therefore is 1.43 times 10 to the 10 kilojoules for 1 mole of fluorine-19 nuclei, which is a tremendously large quantity when we consider that the enthalpies of ordinary chemical reactions are of the order of only 200 kilojoules. The procedure that we have followed can be used to calculate the nuclear binding energy of any nucleus. As what we have noted, this nuclear binding energy is an indication of the stability of a nucleus. However, in comparing the stability of any two nuclei, we must account for the fact that they have different number of nucleons. So for this reason, it is more meaningful to use the nuclear binding energy per nucleon, which we define as the binding energy per nucleon is equal to the binding energy divided by the number of nucleons. So for the fluorine-19 that we are working on, the nuclear binding energy per nucleon is given by 2.37 times 10 to the minus 11 joule divided by 19 nucleons, or 1.25 times 10 to the negative 12 joules per nucleon. The nuclear binding energy per nucleon enables us to compare the stability of all nuclei on a common basis. This figure shows the variation of nuclear binding energy per nucleon plotted against the mass number. As you can see, the curve rises rather steeply. The highest binding energies per nucleon belong to elements with intermediate mass numbers between 40 and 100. And are greatest for elements in the iron, cobalt, and nickel region, or the group 8b elements of the periodic table. This means that the net attractive forces among the particles, protons and neutrons, are greatest for the nuclei of these elements. This ends the first part of Module 4.3. Should you have clarifications, you may ask your respective teachers about them. Thank you for listening.